everyone, and welcome to the Aircraft Certification channel. I'm Clarissa Fedel, and together with Rafaela Caillaux, we create this space to share our experience with aircraft development and certification and to allow other professionals to do the same. So if you like aviation, subscribe to our channel and click in the notifications button to be aware every time that we upload a new video. In today's video, Rafaela talked with Ansel James about uncontained engine rotor failure. That's a particular risk mentioned in Ansel's last video that you can see through the link that will appear on your screen. You also can contact Ansel directly through the link in the description area. Ansel starts talking about the type of failures that must be considered and how the analysis is performed, referring to the applicable regulation and guidance material. He also mentioned about the challenges during the process and the importance of being constant contact and interaction with the designers and the development engineers. And last but not least, Rafaela and Ansel discussed the eVTOL and how the rotor non-containment can be addressed considering the numerous engine installations in different configurations and the impact in the upcoming regulation. But to see that, you need to get to the end. We are hoping to receive your feedback in the comments area, and if you like, share with your friends. I hope you like your flight with us and enjoy your journey.
Hello everyone, I'm Rafaela Caillaux, and today I'm here with Ansel James. Ansel is here again, and today we are going to talk about uncontained engine rotor failure. If you haven't seen his video before, you can click in the link and access the particular risk analysis video. So Ansel, can you start introducing yourself to the audience?
Yes. Hi, my name is Ansel James. I've been in the aviation industry for the past 21 years in senior engineering and management roles, involved in aircraft development at an aircraft manufacturer. Also I've been a Powerplant engineer at Alaska Airlines and a senior engineer at the FAA, involved in certification and continuing operational safety.
Okay, so you've been through a lot already. And I would like to start this conversation asking you what's the difference between the rotor burst analysis that we often hear about during an aircraft development and uncontained engine rotor failure analysis.
Okay, well, engine uncontained rotor failure compared to rotor burst analysis. The rotor burst analysis can be seen as a subset of uncontained engine rotor failure, to the extent that UERF, or uncontained engine rotor failure, also includes analysis of fan blade failure in addition to rotor failure.
Okay, and what is the uncontained engine rotor failure analysis? Okay,
so the engine contains many high energy rotating parts. So the failure of these parts into fragments, if you can imagine the fragments escaping, puncturing a hole in the engine casing and potentially damaging the aircraft. The analysis of the damage, potential damage to the aircraft, potential damage to the systems that are impacted by the fragments, and then also being able to understand the residual risk remaining after the mitigations for the impacts are taken. With engine rotor burst, you can't completely eliminate the risk. So you have to understand the remaining risk and see if that remaining risk is within an acceptable level.
Okay. So can you describe what are the high energy parts on the engine that you have to consider?
Yes, the engine has different sections. There's a fan section, a compressor section, the combustor section, and then the turbine section at the rear of the engine. All these sections, they contain rotors. So the rotor is the disc. There's a rotating disc in there that the fan blades are attached to, that the fan blades and the compressor blades and the turbine blades are attached to within these different sections. Now these rotating components have a lot of high energy. They're under a lot of pressure as the air is compressed going into the engine. They're under high temperature in the combustion section and then at the turbine section as well. So these components, they can fail. They can fail in different ways for different reasons. One of the most common ways for the rotors themselves to fail, they can fail because of metallurgical issues and metallurgical anomalies within the actual base metal, within the material. Also the blades as well, they can have metallurgical anomalies, inclusions. Depending on how they're manufactured, they can be manufacturing defects in how the base metal is treated, the heat treats and so on. That could initiate failures at the intergranular level of these components. Also, the failures can be precipitated by damage either during production or maintenance. If the part gets a nick or a dent, that can be a stress concentration point for potential crack generation and propagation to the point where the disc might fail. Normal way for the discs to fail, it can fail into 3 components. A 1/3 disc is failure is what we would call it, when the disc, because of how it fails, it splits along one line and then it fails into 3, and those 3 parts can be ejected from the engine as the engine is in operation. And that's what we look at is one of the things we look at is the trajectories of those fragments after they leave the engine, potentially damaging the aircraft. They can also fail and have intermediate fragments. It means you could have pieces of the rotor and pieces of the blades still attached, and we can look at that as well, its impact on the aircraft. And also small fragments, the shrapnel. In addition, we also have the fan blades that can fail and be ejected from the engine as well, that we need to address during the course of the uncontained engine rotor failure analysis.
Okay, so basically you have to address every rotating part inside the engine and to see the trajectories and how it's impacting the aircraft.
Yes, because these parts, when they fail, they can also another way it can fail that I forgot to mention just now is it can also fail if you have a part that's internal to the engine that fails. Like for example, there was an A380 that had an uncontained engine rotor failure over Indonesia a number of years ago.
Okay.
And that was because an oil tube failed within the engine. Oil was leaking into internal to the engine, caused the fire, and the fire damaged the rotor to the point where it split. The rotor couldn't handle the thermal loads and it broke apart.
Okay, so that's another type of failure that can happen.
Another root cause of the failures.
And you're talking about the engines itself or themselves, but what about other rotating parts in the aircraft? Do you consider these parts as well?
Yes, the aircraft also has other components that have high energy rotating parts. Components like pumps, fans, generators, the cooling fans, they're high energy rotating parts. Now the energy is nowhere as high as the energy that would be in a fragment from a rotating disc or fan blade, but they still must be considered. And the way this is done is by showing of compliance to a specific regulation, which is 1461.
Okay.
And compliance can be shown by showing that the fragments can be contained within the casing or the housing of the unit itself. And also, another way the compliance can be shown is when the part is installed, if failure of the part, and if the high energy parts do escape, like the tiny cooling fan blades and so on, if they do escape, they don't cause a hazard to the aircraft. So there are a number of different ways that compliance can be shown for those components to the regulation 1461.
So the 1461 addresses all those other rotating parts.
Yes.
And what is the specific regulation for rotor non-containment?
Okay, for the engines.
Yeah, for the engines.
Now this it's 25.903D1. Basically says that you have to show that you've minimized the risk of the hazards to the aircraft from an uncontained rotor failure. Now the guidance that is provided to be able to show compliance to this is included in the Advisory Circular 20-128A.
Okay.
Basically it says that you understand what the failure modes are that could lead to catastrophic failure conditions within the aircraft, and you generate a rotor burst model to understand the risks that you have based on your engine configuration and the aircraft architecture and layout. You do a safety analysis based on that, and then the residual risk, because you can't completely eliminate the risk to the aircraft from a rotor failure. You have to understand the risk that remains and see if that remaining risk is within an acceptable level.
Okay, and what's the relation between this requirement and the safety requirement from the 251309? So how they are connected?
Well, there's a difference in that the 903D1 is a specific requirement. 1309 is a general requirement. So 1309, you have to reduce the with 1309 you do an assessment and you make sure that the risk of catastrophic event is less than 10 to the minus 9. With 903D1, you have to minimize the hazards.
Okay.
You have to minimize the hazard and basically understand your remaining risk. By minimizing the hazard, you can potentially reduce the risk to far below 10 to the minus 9, which you're obligated to do under the term minimizing, because what minimizing means is you reduce the risk to a practical, you take all practical measures. So if something is practical, then you are obligated to do it. Whereas in 1309, if you get the risk to below 10 to the minus 9, then you may not be obligated to continue to minimize the risk. But with 903D1, you have to do everything that you can possibly do to reduce the risk. And that includes making small changes where necessary and doing everything you can to show that it's everything practical. And then you have to demonstrate that to the authorities. You have to show them that you've done everything and there's risk, although there may be risk remaining, that's acceptable.
Okay.
With 1309, you have to eliminate the single failures.
Okay, so you could have a single failure leading to a catastrophic event that you couldn't have in the 1309, but on the other hand, you need to show that you've done everything that was in your power to minimize this event from happening.
Yes,
not only the event, but the consequences of the event, right?
Correct. So by minimizing, you remove the risks, and one of the risks that is you minimize the risk. Sorry. So one of the risks that will always remain is hitting the other engine, because with the model that we use and the assumptions that we make for the rotor burst, the UERF analysis, is that those one-third discs, the one-third disc fragments that I described, they has infinite energy. So there will always be a trajectory, maybe multiple trajectories from different rotors that will impact the opposite engine and the fuel line to the opposite engine. So you have the potential to lose both engines, and there's no way you can completely eliminate that risk. So you would use that risk in your residual risk analysis. You consider that risk.
Okay, so how is the analysis itself performed? How do you do that?
Well, the analysis is performed typically pretty early on you begin considering the analysis early on in the development of the aircraft. As normal steps in the aircraft development, you would understand what specific system failures and combinations of failures would lead to catastrophic failure conditions. Then you would use the preliminary system safety assessment to develop your safety requirements to help mitigate those risks. Safety requirements, things like redundancy, separation, isolation, and protection of the systems, because now you know what combinations would lead to catastrophic failure conditions, so you try to mitigate that. So understanding that, you would develop your aircraft architecture and the systems layout from that. Then you would develop your rotor burst model and superimpose that onto the aircraft layout, showing which would incorporate those redundancies, those safety requirements. And then you would look to see if there are other areas or other specific scenarios based on the rotor burst fragment trajectories that would violate that. So you would have, you'd be looking for places, even though, for example, if you separate two wire harnesses that together would, if they both failed, would cause a catastrophic failure condition, even if you separate them to other different sides of the fuselage, there's a potential that they can be hit by the same fragment, and then they wouldn't be independent of each other as far as failure is considered. So then you would have to understand how far you would need to separate them, in which direction, and so on, or maybe you need to completely reroute those wire harnesses or the signal to be compliant with to meet the rotor burst requirements, safety requirements.
Okay, so it seems like it can also create a lot of changes in how the things are routed in the aircraft. So that's why it's important to happen, or at least to start this analysis early on in the development process, right?
Yes, because the analysis itself is very tedious, and I'll describe how the analysis occurs a bit later. But in defining the model itself, you would look at all the individual rotors, understand the fragment trajectories from those rotors, the failure of those rotors, where they would go, and then understand the systems that are impacted. Now let's talk about the actual the model.
Yeah, that's what I was gonna ask. How does the model works?
Yeah, so the way the model works is, let's talk about the rotor fragments. So the rotor, it spins basically around the axis of the engine. So you have the axis of the engine, you have the rotor spinning like this. So when it fails, the parts are going to be through centrifugal force, the parts are going to be ejected perpendicular to that axis. Now, with what we have seen is that you need to take into consideration a certain spread angle.
Okay.
Meaning that the rotor can be, when it's ejected, it might not be ejected completely perpendicular to the axis because it's under different loads. So it may be ejected up to 3 degrees or up to 5 degrees forward or aft. So you have that either a 6 or 10 degree spread angle there that you have to look at. And you use either the 3 degree or the 5 degree depending on which model you're using, and I'll explain that in a minute. But you would look at that individual rotor, the fragment, based on the size of the fragment and the dimensions of the fragment. For the 1/3 disc, you would look at that trajectory as it extends out into space through the aircraft. You understand what systems are impacted and try to mitigate. So with that, you also we'd also look at the fan blades. The fan blades now can be ejected. The fan blade fragments from damage that can be caused by intergranular intergranular failures, or just from impact due to FOD or any of those reasons. Those fragments can be ejected forward of the engine. So when we look at the fan blades, we look at a trajectory that's 15 degrees forward.
Okay, so you consider a little bit more
Yes.
spreading is higher.
Yes, yes. Now, even though with the fan blades, during the course of the engine development, the fan module is tested to contain the fan blade failure. So the engine module, the engine supporting structure are tested during engine development to show that the retention system, the containment mechanism, can contain the fan blade. But as I mentioned, the fragments can be ejected forward.
Okay. And what about APUs? Do you have to do the same analysis, or are they considered the same as engines?
Yes. So APUs, you have to do an analysis. Now, the analysis that you have to do depends on what the manufacturer of the APU, what analysis they did at their end. If the manufacturer of the APU has shown that the large fragments can be contained within the APU housing, then you as an aircraft developer, all you have to do is look at the small fragments.
Okay.
But using the same logic, that the small fragments will be ejected within a certain spread angle, and it can potentially damage, because the APU is towards the rear of the aircraft. The fragments can potentially damage the flight control surfaces to the rear of the aircraft, such as the rudder and the elevator, and any systems that may be back there. So that has to be assessed, and that's part of also the UERF analysis that's described in the AC 20-128A.
Okay. And is there a difference between the fan blades and the rotor blades analysis?
Just in the actual the spread angles, but also with the fan blades, and actually the intermediate fragments, mm-hmm. they don't have infinite energy, so they're not considered to have infinite energy. So what happens with those are that the fragments themselves, the trajectories, the damage area is dependent on the size of the fragment, which is a proportion of the total dimensions of the fragment. For the fan blades, it's 1/3 of the tip distance, the length of the fan blade. You would look at the mass of the fragment, and also the rotational speed, the red line rotational speed. So that gives you the fragment size and the fragment energy. And the same for the intermediate fragments, where you would assume a part of the rotor and a part of the blades where it's connected would escape with a certain amount of energy.
So you need to consider the amount of energy of each specific fragment?
Yes, for each rotor it'll be different, because the rotors are different sizes, if the rotors are different sizes. And then you would understand how far it would take going that fragment penetrating into the aircraft and the systems before the energy is completely dissipated. So you can protect to a certain extent with the use of shields and so on, or just by separating. But again, the assumption for the fan blades and the intermediate fragments is that those fragments have energy that can be dissipated by impacting the structure and so on.
Okay, so you have to go one by one and calculate the energy and do the assessment.
Yes, if that's the model you decide to use. Now, when I mean the model, you always have to do that for the fan blades. But with regards to the intermediate fragments, there is an alternate model that can be used that's specified in the AC. Okay. The alternate model, the normal model is to use a 3-degree spread angle for the engine, for the rotors. So each rotor having infinite energy with a 1/3 disc size fragment, plus or minus 3 degrees. If you change that spread angle to plus or minus 5 degrees for the 1/3 disc, and then you take that across all of the discs of the engine, then you don't have to do the assessment for the intermediate fragments.
Oh, okay, so there's kind of a simpler way to do the analysis if you consider this alternate model, which seems to be more conservative, right?
Yes, and it's a little bit given the fact that during the course of aircraft development, there are a lot of changes and a lot of reassessments that have to occur based on changes in aircraft layout, changes in the component functions and different failures that can occur by driven by different changes in different hardware, different relocating hydraulic lines, wire harnesses, and so on. Being able to continually reassess from a rotor burst perspective, the impact of that is something that's ongoing. So if you just use the alternate model, which is the 5-degree model, it might make it a little bit easier. Some manufacturers may find it's easier to do that.
Okay, so now that you have at least chosen a model and defined your threat areas due to the trajectories of your blades or at least fragments, what's next? Then what do you do with this information?
Then afterwards you would begin your safety assessment, your safety analysis. To do your safety analysis, you would need to look at each fragment trajectory that impacts the system. And this is the tedious part of the analysis. This is the more difficult part, where your organization and your structure for doing the analysis really comes into play.
Okay.
Because you have to, for each rotor, you have to look at, with the 1/3 disc, you have to look at the fragment trajectories as it hits, project out into space for any given translational angle, because when the disc fails, it's assumed to fail anywhere within the 360 degrees and also anywhere within the spread angle. So you have to look at all of those individual trajectories that can impact the system. Then you see if another system is also impacted with that same trajectory, and if it is, if that can potentially cause a catastrophic failure condition. Now, in addition to, and then you would have to mitigate that risk either by changing the function of the system, by separating, adding redundancies and making sure that they're separate, at least by the dimension of the disc, so that one disc fragment can't hit both at the same time. Adding some kind of or changing the signals that go along the wires or so on. There are different things you can do to mitigate that risk. But then after that, you would try to continually minimize the risk until there's nothing that you can practically do that would prevent you from ending up at a catastrophic failure condition. So you keep doing the iterations, moving things around, and also ensuring that other rotor burst fragments don't negate the activity you've just undertaken to mitigate the risk.
Okay, so it's like an iterative process. So
Yes.
how many times do you run this process throughout the development?
Well, you start off by understanding what you have, your baseline, and then as you make changes, you would look at those changes individually. As changes in the components, as you have changes in the functions of the components and the locations and so on, you want to continually show that you've done everything you can to mitigate the risk of a catastrophic failure condition.
So, but what about if you change something outside of that threat zone? Is that okay if you change a box in the tail of the aircraft? Do you still have to perform the analysis, or no, you're safe?
Well, you would need to understand how that box interfaces with any systems that are within the threat zone. So if that box sends a signal, or a signal is received by that box that is in a wire harness within the threat zone, if that signal changes by changing the box that's outside, you need to understand if that signal, that change in signal or change, results in a catastrophic failure condition, or if it removes a failure condition that you may have addressed in the past, or if it changes something that you've done. And also you need to be able to understand when that fragment, any given fragment, when it does hit a system that, and it does not end up in a catastrophic failure condition, you need to understand that if you now put another system behind that it will end up in a catastrophic failure condition. You need to understand, so basically let's keep out of that zone where that fragment is going to do that. And that's, you have multiple fragments that can have the same effect. So you have to do that for every possible potential fragment going in that area.
Okay, so you have like those threat zones that are directly impacted by the trajectories of the fragments, but still, if you need to change something outside of that zone, you still need to consider in the analysis, right?
Yes.
Okay, and now looking into the future, and we are seeing that many companies are developing the aircraft that flies vertically, takeoff and landing.
The eVTOL aircraft.
Yeah, the eVTOL aircraft. How do you see this impacting those aircraft? So how does this analysis can impact, since they don't use a conventional engine?
Yes, so there are lots of challenges with these new vertical takeoff and landing, especially the ones that are powered by electric propulsion units. I would imagine that compliance would be shown for the hazards to those types of aircraft. Mainly they're Part 23. They're all right now Part 23 aircraft under 19 passengers and so on.
Okay.
The regulation that would drive them to show that they would have to comply with is 23-2400. It basically says that you have to minimize the risk of hazards to the aircraft from the propulsion unit, which would include the rotors as well. I believe that you would be able to show that the propulsion unit housing itself would be able to contain any failure of any of the high energy rotating parts within it. I think that would be the easiest way to do it. Also, it would be up to the manufacturers to develop means by which they can show that there aren't any hazards for the propulsion unit on the aircraft. Now, the rotors themselves are a slightly different story, simply because of the many different types of rotor configurations and how the rotors can operate in service. You know, obviously the number of rotor blades is different for the different configurations. The location of them are different. Sometimes the rotor may be shrouded. It may be like a ducted fan. It may have a shroud around it, in which case rotor failure, they just have to show that the shroud can contain the failed blades. But for the open rotor designs, and some of them, they translate during flight. They can go from vertical to horizontal and anywhere in between. The manufacturers would have to develop their own models to show the impacted areas. And then also, depending on the phase of flight, they'd have to be able to show that for their configuration that the aircraft would remain safe regardless if considering rotor blade failure.
Yeah, it seems like that since they don't have those like infinite energy fragments to deal with, it seems it could be a simpler analysis. But on the other hand, they don't have a structured process as the Part 25 does with the conventional engines and with the AC and so on. So how do you see that the authorities would have to manage to, do you believe that they will issue some kind of guidance material?
Yes, I think that based on right now, the requirements and the special conditions aren't very they aren't prescriptive, and that's for a reason, because they don't want to limit the creativity of the manufacturer of these these aircraft at this point. That's why the authorities will have to work very closely with the manufacturers and having them demonstrate to the authorities that they are given the different configurations, the different materials, the different number of blades and so on, that the manufacturers will have to work with them very closely to show that for their configuration, they can show that there are no hazards, or they can minimize the hazards to the aircraft. Now, as far as the authorities presenting guidance, I believe that what will happen is that as the industry matures, as the different authorities get more exposure to the different designs and the different ways that the manufacturers would show compliance, the different models that they come up with, they would get a better understanding of what makes sense.
Okay.
They would get a better understanding of the best design practices. They would get a better understanding of the best principles that would be used as both the industry and the authorities gain more experience. And then what I believe would happen is the authorities would take the best of that experience and maybe put it in a form of performance-based guidance to the manufacturers. And I would hope that it wouldn't end up as a prescriptive guidance, simply because you don't want to drive the manufacturers into doing one thing or the other, but leave it up to them to show how their configuration is able to minimize the hazards to the aircraft.
Yeah, and since it needs to be applicable to many different configurations, it's hard to have a prescriptive guidance material.
Yeah, and for Part 23, that's why there was a Part 23 rewrite for the FAA.
Yeah.
And ES has followed as well, that having prescriptive guidance is very restrictive.
Yeah.
So it's more performance based now. So you show us, what needs to be done. This is the intent of the regulation. You show us how you can do it, as opposed to giving direct instructions on how to show compliance.
And do you foresee new types of evaluation being needed? Because I can imagine that with I've seen some aircraft with blades underneath the aircraft, and maybe they could hit someone on the ground, or they could hit a car. So they're flying in urban areas. Yes. So how do you see this?
Yes, you're absolutely right. These new aircraft are designed to operate in urban environments. Typically, Part 23 and Part 25 aircraft, they transit these areas, and then they fly well above.
Yeah.
But eVTOL aircraft, they're designed to be operated within urban areas, in close proximity to houses and people and traffic and so on, relatively close proximity. Another consideration is the fact that these aircraft they're not pressurized, they don't go very high, as far as, maybe not that often above 12,500 feet, which is the limit for pressurization for an aircraft and needing oxygen and so on. So most of them will live basically in the zone where you have a lot of birds.
Wow.
Especially in urban areas, you have a lot of trees, a lot of birds in these urban areas, and the manufacturers will have to work with the authorities again to show how living in these environments with their different configurations, given the probability of interacting with the birds, can still result in a safe aircraft by minimizing the hazards to the aircraft, either through design or operation of the aircraft. Software to help see and avoid, to help the pilot see and avoid, and do different things.
Yeah.
To be able to minimize the risk.
Yeah, so maybe the engine rotor failure is not as a big concern as it is in the Part 25 or conventional engine aircraft, but then bird strike would become more relevant in these aircraft. And
yes, so the fact that these new eVTOL aircraft operating in an urban environment and flying a larger percentage of their time in the airspace inhabited by birds does increase the risk for potential bird strikes and ultimately maybe even rotor blade failure because of these bird strikes, these impacts with the birds. Now, this will have to be mitigated somehow by the manufacturers as they show that they can address the hazards, the risks from the hazards to the aircraft from the birds by doing different things. I think being as creative as they are in developing the aircraft to begin with, understanding the different material properties, the different characteristics, the different failure modes of the rotors themselves, they should be able to somehow mitigate the risk of the rotor blade failure through different means. I wouldn't hold the authorities to mandate certain methods of mitigating the risk. I think that just the manufacturers themselves, they will be able to develop models and develop assumptions that maybe at this point in time the authorities don't have much experience with, to be able to use those models, different assumptions, different risk methodologies to show that the aircraft can be safe even operating in this in the urban environment with the different risks, that the different hazards that typical aircraft Part 25 and Part 23 aircraft would not see. So I think it's not a difficult hurdle. It'll be challenging, but not insurmountable.
Okay, yeah, let's see what's coming up. And maybe we should do another video on the bird strike specifically for eVTOL.
Yes, we can definitely talk about that as well.
Okay, let's think about it.
Yes.
So Ansel, thank you very much for being here with us
Thank you for having
again.
me.
And hope to see you again. If you want to contact Ansel directly, his link will be in the description area. So thanks for following us and see you in the next video.